Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we are discussing the particle capture mechanism during air filtration. So, these are inertial impaction, direct interception, Brownian diffusion, gravity settling and electrostatic charge. So, electrostatic capture with the help of electrostatic charge, that helps in capturing the very smaller particles, that we will discuss in detail. Now, the particle capture mechanisms, that is inertial impaction. If you see from the figure here, fiber surface and particle moving at high speed with a higher inertia, and it will strike the fiber surface. So, it is important at high and medium velocities for microparticles. So, microparticles are moving at high speed or medium speed along with the air stream, and during its path, so this is a filter media. So, smaller particle at high speed it is moving. So, it will strike the fiber, and that impact will actually reduce its speed, and the air is flowing out, but the particle is settled within the structure due to the inertial impaction. It will lose its energy and it will get settled within the structure. Then direct interception. So, particle little bit smaller size, okay, where the particle's diameter and this filter diameter are comparable. That means, diameter of pore, their smaller particle will try to move along with the with the airflow, because small particle with a lower, it will follow the air path, but air will flow at different direction. During its path, it will get some place where it will be trapped by depth loading, like a smaller size. So, smaller pore size, there it will get trapped and it will be separated from the air stream, that is called direct interception. Direct interception is possible where the particles should reach a position where the size of the pore is equal or smaller than the particle. So, there only it will get entrapped, and Brownian diffusion is basically for very small particle with a like nanoparticles, and there the speed of the the air flow rate will be very small, very low small air flow rate, and particle will move in the Brownian motion. It will make a Brownian movement, and suppose this is a filter and it is moving throughout the thickness. Now, a very small particle is moving with a Brownian motion. During this movement, there will be a position, there will be a point where the particle will strike a fiber surface and get settled there, because the speed of the air is very small. So, very low speed, and their particle will go in Brownian motion and get settled on the surface of the fiber. And another is that gravity settling, where large particles it will not be able to follow the air path, because air will not be able to carry that large particle, it will get settled within the structure. Okay. That is even before striking the fiber it will get settled. And last one is that it is a electrostatic attraction. So, when the fiber is charged, the electrode charged, so and the opposite charged particle will get attracted on the surface. So, that is actually electret filter, and here if we have larger size of fiber, the coarser fiber, the chances of charge development will be more, and there will be higher probability of particle get settled and filtration efficiency will be higher. So, as we are using the coarser material, their air flow rate will be higher. So, pressure drop will be low. So, at lower pressure drop, at low and medium velocity, all particles can be charged, can be filtered out. So, these are the broad filtration mechanisms which is actually followed during the air filtration. Now, one is that sieving process. Basically, straining and sieving is not the filtration, that we should be. So, straining and sieving is not filtration, it is only stopping the large particle larger than the pore size, okay. And we do not need any filtration mechanism. It is a metal, fiberglass, so like a metal mesh is used. This is only stopping the fiber from moving out, that is a sieving process. It is different from the actual filtration. So, here we get the MERV rating 4 to 6, it does not follow any filtration mechanism. So, next is that we can have very high flow rate. Sorry. Next is that inertial impaction. So, this particle impacted the fiber surface, this is fiber surface, and it lose its energy and it gets settled within the structure. So, here mainly larger particle size more than 1 micron, so that we get the inertia. So, this effect increases with increasing the velocity and particle size. So, if we increase the velocity, air velocity, then particle will follow at higher speed and it will impact the fiber surface, and with the larger surface, larger fiber diameter, coarser fiber will have higher probability, and also for larger size particle will have higher mass and it will have higher inertia. So, that also inertial effect will increase. So, filter opening size is that its efficiency is MERV rating 6 to 8. So, media velocity 100 feet per minute. So, this is used for plated type of filter, inertial impaction. Then interception for smaller particle size, typically between 0.5 to 3 micron. So, here the particle moves and it moves with the air flow, it follows the air flow, and inertial impaction as I have already mentioned. So, that it does not follow the air flow path, because it has got higher inertia because of higher particle size, mass of the particle, higher speed. So, it will directly impact the fiber, it will follow the straight path, not the, it will not follow the air path, but smaller particle with a lower inertia, it will follow the air path. So, air, it will travel the air path and it will be trapped where, somewhere where the size, that is the distance between the fiber, this is another fiber, distance between two fibers are smaller than the particle size, that will be trapped, it will be intercepted there. Okay. So, this effect increases with increase in particle size. So, as particle size increases, that if at all it follows the air path, the chances of trapment will be more, and decreasing fiber diameter. So, decreasing fiber diameter means the it will have more chance of having smaller pore size. So, there it will get trapped. So, the filters which operate in this interception mechanism, back filter, rigid filter, vivet filter. So, these are the different types of filter which works on this principle, and it can give the efficiency MERV rating 9 to 16. So, 92% efficiency, and media velocity is little bit lower. So, here we have less than 35 the air velocity. Now, diffusion, you can see that Brownian motion is there, and during this movement, during its path, somewhere it will get, it will strike the fiber surface it will strike the fiber surface and get settled on the fiber surface. So, it increases with increasing the fiber diameter. So, higher the fiber diameter, so more will be the chance of getting settled on the fiber surface, and reduced velocity. If the velocity is increased, this particle will simply follow the air movement, air path, not the Brownian motion. Brownian motion will only happen if the air velocity is low. So, that in that case the particle will try to follow that its random path, and particle size, reduced particle size, smaller particle, the smaller the particle, more will be the Brownian diffusion. Okay. So, it happens with all filter, any filter we can use, because that it will strike, chance of striking will be there, but more prominent as efficiency increases. So, if we want to have higher filter with higher efficiency, their Brownian diffusion will be there. That is actually next method is the electrostatic charge. So, we charge the fiber with positive sign, positive charged fiber, and it will attract the negative charged fiber on the surface. Okay. And this, the effect of electrostatic charge will, attraction will increase with the increasing the fiber, actually it is increasing the charge of fiber. If we have more charge, there will be more attraction. Charged particle, if we have if we increase the charge of particle, then it will be more. Decreasing the particle size, if we decrease the particle size, that means it will have lower inertia, that will get attracted and at lower velocity. So, if the velocity is low, then it will actually get attracted with the electrostatic charge. If the velocity is more, then the air will try to take the particle. So, and even the particle diameter, so fiber diameter, if it increases, then also there will be higher chance. So, this mechanism we can control by controlling all these parameters. So, that larger fiber diameter is normally chosen due to low cost and resistance to air flow, low resistance to air flow. Okay. So, filters using large diameter fiber media, which actually where the lower pressure drop is required, there to increase the efficiency they rely on the electrostatic charge. So, there will be some filter where we do not we cannot have very compact fiber, compact structure. In those case, large diameter fibers are used. So, to enhance the filtration efficiency, we charge the filter with electrostatic charge, but mainly we can think of the in the automobile filter we can use this type of electrostatic charge. So, the problem is that it will lose its electrostatic charge with the time. Okay. So, it can be used for back filtration, rigid pleated filter, MARB 9 to 15 we get from the electrostatic charge. Now, we can see the with the particle size what is the type of efficiency we get. Here if you see that, as we have discussed, we cannot have only one mechanism is followed at the time. So, more than one mechanisms are followed in during the filtration process of particle filtration. Now, here the particle size in micron in the x axis and efficiency. Now, one by one let us see the inertial impaction. Inertial impaction will be more if we have larger particle size. So, filtration efficiency at lower particle size, inertial impaction is less, there is no it effectively it does not filter, but as we go on increasing the particle size, inertial impaction is increasing. Interception also increases with the increase in particle dimension. Like higher particle size, that means more chance of it will get entrapped within the structure, intercepted within the structure. And diffusion, if you see diffusion as we have discussed. So, as the fiber particle size reduces, the Brownian motion will be higher, and through the diffusion the efficiency will be higher. So, if we have very low particle size, lower the particle size, higher will be the entrapment. So, and higher particle size, there is no that Brownian motion will be there, typically above say 2-3 micron. So, there that does not exist. So, at lower particle size, this diffusion exists. Similarly, for electrostatic charge, lower the particle size, higher will be the electrostatic charge effect. But here we can see we can enhance the filtration efficiency to a certain extent. So, if we see only the electrostatic charge, considering that there is no other mechanism working at this point. So, there we can have typically around 30% maximum, even if it is a very small particle. So, that range is there. Okay. But through Brownian diffusion only we can achieve very high filtration efficiency. Next is that diffusion So, 4 mechanism we have discussed, and now we can see the plot. This is the plot where efficiency without static charge. So, if we do not consider the static charge, if we consider only the interception, inertial impaction and diffusion, the typical plot is this, means that if we go for the particle size lower side, lower than 0.1 micron, there the Brownian diffusion will dominate and we will get the filtration efficiency typically around say 70%, 70-75%. But if we go on increasing the particle size, the Brownian diffusion will reduce and inertial impaction effect is not there, and interception will gradually increase. So, that is why little bit drop in the filtration, overall filtration efficiency. And as we go on increasing the particle size, although Brownian diffusion is not that effective, but the interception and inertial impaction, due to that the filtration efficiency will increase again. When we charge the particle, the filter with electrostatic charge, we can get the similar trend, but overall charge will be, overall efficiency will be increased. So, for any filter, if we use the electrostatic charge, so and in that case we can achieve higher filtration efficiency, typically around 100% filtration efficiency we can achieve, keeping the air flow rate or pressure drop at the lower side. Now, this is the case here, and where in normal, on the normal say spun bonded, we can have nanofiber layer also to enhance the filtration efficiency. Okay. Now, you can see here surface filter and depth filter and retention efficiency. So, this is the surface filter, that means particle size when it is increasing and it is more than the fiber that is pore size, immediately the filtration efficiency will increase, but depth filtration it will increase gradually with the particle size. Now, what are the different raw materials? So, raw materials are natural fibers are there, man-made fibers, bicomponent fibers, and different types of fibers are man-made fibers are, you can see then natural fibers like cotton, hemp, sisal, jute. So, all these fibers are used depending on the application. The advantage is biodegradable, these are absorbent and low cost due to abundant availability. Now, man-made fibers, different types of man-made fibers are used depending on the requirement, polypropylene, polyester, polyamide. Okay. So, for high temperature we can use glass fiber. Okay. That is, these are the different advantages. Uniform fiber you can get. Okay. Bicomponent fibers are widely used in case of filter, because the bicomponent fiber can create the stable structure. If we create one nonwoven structure using the bicomponent means fiber combined with a higher melting point polymer and with a lower melting point polymer, and after making the web, if we blow the hot air, the low melt portion will get melt and they will stick to its neighboring fiber and it forms a stable structure, and that will help in retaining the structure. So, if we do not use the bicomponent fiber, the structure get distorted, it get compressed and the structure get compressed, distorted and total characteristics of the structure will change. So, bicomponent fibers are of different types. What are the types? One sheath core type structure. So, core is with higher melting point polymer and this is sheath is with lower melting point, this is maybe polyester and sheath may be with polypropylene. So, after making the fiber and nonwoven structure web, if we melt the polypropylene and then the total structure will be retained, but this polypropylene with the will be fused with the adjacent fiber. Side by side arrangement, there will be segmented pie arrangement, segmented ribbon arrangement, different tipped arrangement, Iceland in sea. So, this type of different this island in the sea. So, this different arrangement is there. So, which will help in actually bonding, and also these fibers may be created which after heating they may create a crimped structure which will be porous. Okay. The constituents are polypropylene, polyester, polyethylene, nylon. So, there are different types of constituent polymers we can use. So, nonwoven technologies are employed, the different types of nonwoven technologies, fiber preparation process, web formation, web bonding. So, these are the different types of nonwoven technology we can use, and all the nonwoven they have the same process we have to form first fiber preparation, and then wave formation will be there, and then there will be one process of wave bonding. Now, the properties of filters are expressed in different ways. So, the filtration properties is expressed in terms of filtration efficiency, penetration, beta ratio, pressure drop. We will discuss one by one. Permeability, filter life, arrestance. So, these are the properties which are directly related to the filtration property, filtration efficiency or filter characteristics. And the filters property, the physical properties are there. So, physical property of filter like any other textile fabric, like basis weight, that is grammage it is called, or basis weight, like typically it is areal density. Caliper, it may call we call it caliper in the filtration term, or it is a thickness, density and bulk, solidity or porosity. That these are very important to know the solidity, density, because they are directly related with the air pressure, air flow rate, the air flow and pressure drop. So, that is why we have to measure this. Pore structure is also very important. Dimensional stability is very important. Mechanical properties include tensile strength, tear strength, bursting strength. So, these are the different tensile properties, because bursting strength is very important, because for high speed air flow. So, fabric should actually retain its structure. Tear strength, these are the test physical and mechanical properties we should test, we should know for a filter fabric. So, let us start with the filtration efficiency. This is actually quantified by the quantity in terms of mass or number or volume of contaminants, of a particles removed by the filter media, which is expressed as a percentage, that is filtration efficiency. You can see this E is the filtration efficiency, N in is the particle coming in from the upstream side, and N out particle is, this is particle, N in is coming inside the, and then N out is particle going out. Now, what is N? N may be the mass, total mass of the particle is coming, or maybe number of particle. So, efficiency it is as percentage, N in is the input, the upstream quantity of contaminants. Like there are, if it is number 100 particle is there, now it is coming, and say 10 particle is going out, 10 particle is going out. So, the particle, this filtration efficiency will be 100 minus 10 by 100, so 90%. So, if that is a total weight is 100 and 10 the going out, the say 100 gram is coming inside and 10 gram is going out. So, in that case also it is a 90% efficiency. So, number out in, that is maybe number or weight. So, the filtration efficiency can be expressed in other terms also, which is known as arrestance. We can express in terms of arrestance also. So, arrestance is used to denote the filtration efficiency when the quantity of contaminants is expressed in terms of mass or weight. So, when we express the filtration efficiency in terms of mass, then we can tell it is a arrestance. It is also its filtration efficiency, but if we tell it is a arrestance percent, then we mention, we actually try to intend to tell that the filtration efficiency is measured based on mass. That is why we express in terms of arrestance, but we can call it, filtration efficiency also. This filtration efficiency term can be used or arrestance can be used, but arrestance if we mention, that specifically we are trying to tell here, it is based on the calculated based on the mass of the particle, and the filtration efficiency we can, when we express in terms of the term collection efficiency, there it specifically we are trying to tell, we have calculated the filtration efficiency based on the number of contaminants. So, in earlier we have discussed, either we can call it as in terms of number or mass. So, filtration efficiency term we can always use, but to differentiate whether it is based on the number or mass, then we can use either collection efficiency or arrestance. Okay. Particle collection efficiency, here as we have discussed, it is based on the number n in, n out by n in. Okay. And here we must remember the total efficiency, it actually it is due to the all the mechanisms, due to the diffusion, impaction, interception, gravitational the mechanism. So, all the mechanisms are involved. Next is penetration. Penetration is the percentage of contaminants, maybe in weight, volume or number, that penetrates to the filter media. That means, whatever it is coming out. So, n out by n in. So, 100, as we have mentioned, 100 number of particles came in and 10 went out. So, here penetration will be 10 by 100. So, 10% penetration is there. Okay. So, from there we can get some relationship as the percent. In is the upstream side quantity in terms of number, volume, weight, and n out is the downstream side contaminants. Beta ratio. Beta ratio is also, it tries to express the filtration efficiency by the term beta ratio. This is the ratio of number of input particles of a given diameter, that is important. So, beta ratio, unlike the penetration and other expression, beta ratio denotes with reference to a particular diameter. Okay. That means, we refer to the ratio with for a particular diameter. Suppose this is the filter media. Now, here say two size we can consider. This is the say 10 micron. Particle and another particle which is say 1 micron. Let us consider the only two particles are there, 1 micron and 10 micron. Now, when it is going out, one micron and the 10 micron particles also have come up. Okay. Now, the number of inputs particle of a given diameter or greater number and to the number of downstream part. Now, here for beta ratio for 10 micron, if we try to calculate, you can see that number of input like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 by say 1, 2, 3. This is the beta ratio for 10 micron. And if we try to suppose here in for 1 micron, we are in input sides there may be 1000 and in output side there may be say 500. So, in that case beta ratio will be beta 1 will be 1000 by 500. So, that is the beta ratio, that is for a particular given diameter or greater. So, that here 1 micron will include the 10 microns also. That means, it will be 1000 plus 11. So, that will be the here say 500 plus say 3. So, 500 plus 3. So, that in that way we can calculate. So, for at different level we can calculate the beta ratio. So, this is actually for largest size we consider at say 10 micron and 1 micron plus 10 micron we have to consider. So, this way we can calculate the beta ratio. So, beta ratio advantage is that it specifies the particle size. So, there we have already explained this thing. And we can get this relationship. So, the efficiency equal 100 minus penetration, that is the that we know it is just reversed. So, when efficiency was 90, penetration was 10. So, 100 minus 10. So, 90 is the efficiency that we have discussed. This is the penetration, this is the efficiency we have got. So, that ratio is here and this is the ratio we can get 100 minus 100 by beta ratio. So, that these are the relationship we can convert the if we calculate the beta ratio we can calculate the efficiency also. Now, pressure drop is again very important parameter here. The pressure drop or differential pressure, it is a resistance of air to flow during the filtration when it is passing through the filtration. So, clean filter starts with the lower initial pressure. As the filter get clogged or particle deposited on the surface, the air flow rate reduces. So, we should monitor it via different gauges to ensure the timely maintenance. So, if the pressure drop is high, becoming very high, then the load on the filter will increase and it will increase the power cost and also filter get damaged. At a given air flow, the pressure drop decreases across the filter, and if we increase the air flow rate, the pressure drop will also increase. So, this is the air filter and air is flowing from upstream side to downstream side. During its flow across the filter side, both the side, there will be a pressure drop. We can get pressure signal here, pressure gauge we can incorporate here. So, this is the showing the pressure drop. Delta P, P1 is the pressure in the upstream side, P2 is the in the downstream side. So, input pressure and output pressure. So, there has to be some pressure drop definitely, because without pressure drop air will not be flowed. So, air flow is actually by the pressure drop. Air is flowing from the higher pressure to lower pressure, and this air flow rate, as we increase, the pressure drop will increase. That is okay. The pressure drop should not be more. So, energy efficiency impact. So, if the pressure drop is increased, so it will increase the energy consumption. You can see higher pressure drop in that will actually HVAC fans, that fan actually it at the higher power will actually it will draw higher power, it will have to work harder, okay, and it will increase the energy cost. A low pressure drop cuts the fan power needed. So, at lower, if the pressure drop is low, then we can save the power. So, if because of the lower energy required, that is why normally we use the variable frequency drive just to maintain the air flow. Okay. Now, this diagram will show the final pressure drop is here. Now, with the increase in pressure drop, the power consumption is increasing. So, that because of the higher pressure drop, we have to keep the air flow rate. So, to maintain the air flow rate, we have to have higher energy, we have to draw the higher energy for the fan, filter life and maintenance. So, as the pressure drop increases, so higher pressure drop, so filter with lower average pressure drop will last longer, and as they hold more dust before reaching the replacement, that is okay. And also higher pressure drop will unnecessarily apply higher load on the filter itself. So, it reduces the charged out by the up to 80%, okay, and maintains indoor air quality. So, lower pressure drop, regular check via pressure gauge is important. Now, you can see the filter life reduces, because higher pressure drop means higher particle deposition, and then also if it is higher pressure drop is there, that means filter also can get damaged. So, filter should to enhance the filter life. So, we should maintain the lower pressure drop. And system performance benefit, you can see optimized pressure drop sustains airflow velocity, minimizing the wear out of the filter component, improving the filtration efficiency. So, we have to always target to keep the pressure drop low. It prevents bypass of unfiltered air, because if the pressure drop is high, that means we have to use the higher fan speed, and in that case the particles can also will have chance of moving along with the air. So, it enhances overall return on investment through lower cost and reliability. So, prioritizing the low pressure drop. So, low pressure drop means there will be porous structure, more porous structure. That is only then we can get the lower pressure drop. So, higher air flow, but which we should do? Should we go for lower pressure drop or higher efficiency? So, that we should optimize, but to some extent we can prioritize prioritizing the pressure drop at the lower stage, okay, lower, which suits the high use setting like urban dusty climate. So, where dusty climate is there, then we should actually use the filter medium with a lower pressure drop. So, optimum final pressure drop is this here, where we can have certain amount of pressure drop to optimize. Permeability is the ability of a filter media to allow the fluid to pass. So, and through its cross section. So, it follows the Darcy's law. Q is the volumetric flow rate, maybe air, or in case of water it can be fluid. So, A is the filter cross section. So, quantity cubic meter per second. So, meter per second, this is the K is the permeability, eta is the fluid viscosity. If the permeability and delta P is the pressure drop across the filter. Now, T is the filter thickness. Now, try to see, this is the speed quantity per unit area, quantity of that air passing through per second per unit area, okay. Any fluid, not only the air, any fluid which is proportional to the permeability. So, if permeability increases, this quantity increases. If we increase the pressure drop, then this flow rate will increase. If the viscosity of the fluid increases, then flow rate will reduce, and if we increase the thickness, this flow rate will reduce. So, we can play with all this parameter to keep the flow rate or permeability of filter media constant. Now, we will let us discuss a few instruments for measuring the filtration efficiency, and we have developed in house this filtration mechanism, filtration instruments. So, we have developed instrument for gravimetric measurement with the vertical orientation, and where we can measure the air permeability of filter fabric, pressure drop created across the filter fabric, filtration efficiency of the filter fabric, cleaning efficiency we can measure. Now, the apparatus if you see, it is capable of measuring the filtration behavior of non-oven, oven and knitted filter. So, any fabric we can test here. Area in our instrument was area of filter media 150 square centimeter, circular cross section. Now, there will be dust feeder which feeds the dust at constant rate, one stepper motor which controls the dust feed rate, attachment for dust dispersion. We have attached one dust dispersion arrangement, when as soon as the dust feeder feeds the dust, it should mix with the air, so that there is no agglomeration of dust particles. Upper vertical pipe through which the air dusty air comes, lower vertical pipe below the in between there will be filter media will be there, vacuum pump to actually suck the air through its vacuum through the dusty air through the filter medium. Up and down movement is there, because to attach the the filter fabric in the system. Inclined tube manometer to measure the pressure drop across the filter pressure drop. Vacuum pump guard is there to protect the vacuum pump, okay. And rotameter is there, fluid for measuring the fluid flow rate. Control valve is there, vacuum pump. Now, see the total attachment here. Here the dust feeder is there, it is controlled by stepper motor or DC motor here, and here attachment of dust dispersion mechanism is there, which disperse the dust and mix with the air. Vertical pipe, the dusty air is coming here, and this is the place for filter holder. The filter is placed here, and the air pressure here is the normal air pressure, atmospheric air pressure. So, we measure the air pressure just after the filtration filter fabric. So, using the inclined tube manometer, which gives the indication of the pressure drop across the filter, and then this is the up and down arrangement, and here we place the filter paper, which actually collect the whatever the filtrate, whatever after through the filter fabric, how much the particle, what are the particles come, this gets actually deposited, filtered at the filter paper. So, here we calculate the amount of dust, mass of dust fed with a certain time, and the mass of dust M2 which is being passed through the filter fabric. So, this from M1 and M2 we can calculate the filtration efficiency based on the mass. So, this is the dust feeder arrangement. Here is the hopper where we can feed the standard dust particle, and here it the motor it rotates at constant rate, and due to the screw thread the dust moves forward, and the speed of the this motor actually controls the dust feed rate outlet, the dust feed, then and here it is mixed with the this dispersed with the in the air. And filtration parameter, air permeability we can test, porosity of the fabric we can test. This is the porosity based on the this standard relationship, which if we know the fabric density and the fiber density, from there using this relationship we can calculate the porosity. And dust loading, dust loading is the dust to the air. So, how much dust loading we can use. So, we can control dust loading should not be more than 5 gram per cubic meter, because it will then the air will not be able to hold this dust. And filtration parameter, phase velocity we can measure, pressure drop we have measured, we have by the we can measure by the manometer. This is the pressure drop, P1 is the pressure in the phase side, and on the downstream side the pressure is P2. Filtration efficiency as I have mentioned. So, weight of dust collected by the fabric and weight of dust fed. So, filter whatever the filter fabric that filter paper the dust with that we can add to this the total dust add to this here. So, that because this filter media we have filter paper we have kept, because just to protect the vacuum pump. So, that is there, and if we add this dust this fabric on the fabric and plus the paper, it should be equal to the dust fed. And cleaning efficiency we can measure by actually reversing the air flow. So, dust removed by dust retained by the fabric. So, that will be the cleaning efficiency. Outlet concentration we can calculate. The outlet concentration C0 is the CO you can say is the ratio of mass of the dust passed through the filter collected by the filter paper. That output concentration we can calculate, that is the ratio of the mass to the volume of the air passed through. So, in the output how much dust is coming out, that we can calculate. So, this is the relationship. MP is the mass of the particles passed by the filter medium and collected by the filter paper, and T is the time, and Q is the volumetric air flow rate. So, this is the instrument which we have discussed based on the mass of the particle, and subsequently we modified this instrument, and which was based on the number of particles, and this we will discuss in the next session. Till then, thank you.